Here we go. Simplifies quite a bit. What we end up with is gamma squared minus omega prime squared minus gamma b over m plus k over m, all of that times cos omega t plus delta, plus 2 gamma omega prime minus omega prime b over m sine omega t plus delta equals 0. This equation this side must equal 0 for all times. This is not true just for any particular time, but for any time we want to choose. Well, let's choose some time where omega prime t plus delta, that argument makes sine equal to 1. In other words, where omega prime t plus delta is 2 pi times some n value, any 2n prime, n is some integer, plus pi. That makes this equal to 1. But when that is true, then the cosine is actually equal to 0. So for some times, this will be 1, that'll be 0, which means this quantity must equal 0. Always, for any time. So what do we have? 2 gamma omega prime must equal omega prime b over m. Well, we could cancel off the omega prime, divide by 2, and what do we have? Gamma, the decay factor that we had for the amplitude, e to the minus gamma t, we find is b over 2m. That tells us how rapidly the amplitude decreases. Great. Now let's try the same trick, but now let's assume that omega prime t plus delta is some factor of 2 pi, 2n pi. But in that case, the sine of omega prime t plus delta will be 0. So in that case, this is 0 and this is 1. And for this to be 0, this must be 0. This term here must be 0. Well, let's put in the fact that we know gamma must be b over 2m. And what do we get in that case? Well, you can do this on your own. It simplifies so that what we find is that omega prime squared must be equal to omega squared, our original omega, root k over m. I'm actually going to refer to that as omega naught to emphasize that was the undamped angular frequency. So omega naught squared minus gamma squared. Very, very simple final result. What is this telling us? Well, let's notice. This tells us how rapidly our oscillator damps out, decreases, the amplitude decreases, which makes sense because the larger B, remember the frictional force was minus BV, the more friction we have, the faster the object will damp out. That makes sense. And so the larger gamma, the quicker the amplitude damps out. And the smaller the mass, the smaller the force, or we should say the smaller the mass, the less force is required to damp it out, or the faster the damping force will slow it down. So that makes sense. And then what is this telling us? If omega naught is the frequency of the oscillator with no damping, the frequency with damping is less than that by a factor of, or the squared is by a factor of gamma squared. In other words, the damping decreases the frequency of oscillation. Well, that kind of makes sense. So that we would expect, say, with no damping, we get some oscillation like this. But with damping, the damping slows down the motion. It makes the oscillator move more slowly, you might say. And so it's going to oscillate at a longer wavelength or smaller angular frequency. Okay, very, very good. Let's take a look at some other aspects of these results. Let's look at the total energy of the oscillator. The total energy, E, is going to be the kinetic plus the potential, K plus U, or 1/2 mv squared plus 1/2 kx squared. Again, using those forms that we have, x is a e to the minus gamma t cos omega prime t plus delta. V was that messier thing with the two terms after differentiating. We stick all those in there, gather similar terms together, and what do we end up with? We end up with 1/2 m omega prime squared a squared e to the minus 2 gamma t. So we end up with e to these terms of e to the minus 2 because we are squaring e to the minus gamma t multiplying by another e to the minus gamma t. So all of them have these e to the minus 2 gamma t terms. Plus m gamma squared a squared e to the minus 2 gamma t cos squared omega t plus delta. plus m gamma omega prime a squared e to the minus 2 gamma t sine omega t blah, 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 cos blah, 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 blah. Okay, good. There we go. That's the energy. It's very complicated. It's got a very complicated time dependence as it is oscillating at various points in the oscillation. But let's look at what's the average energy. In other words, we know it's oscillating up and down, and as it's oscillating up and down, it's sometimes going to have a little more, sometimes a little less energy. The way that it decreases, not more energy, it's always decreasing, but the amount that it's decreasing kind of fluctuates. So let's look at what's the average over each oscillation. So we're going to look at how do these oscillatory terms, what are the averages of those? So what's the average energy? Okay, well this does not oscillate, it doesn't have a sine or cosine term, so that's just going to give us a 1/2 m omega prime squared a squared e to the minus 2 gamma t. Then we've got a cos squared term. What's the average of cos squared? Well, we know that cos squared plus sine squared equals 1, and we could guess that the average of a cos squared should be the same as the average of a sine squared. So if they add together to give us 1, each must be 1/2. So the average of cos squared, we could guess, and it actually turns out to be correct, to be 1/2. So we end up with a plus 1/2 m gamma squared a squared, whoops, e to the minus 2 gamma t. Now, what's the average of a sine times cos? Well, while cosine was always positive, it didn't have any negative terms to cancel out. Sometimes sine cos will be positive, sometimes sine cos will be negative, and it turns out the average is 0. So when we average this part, it doesn't contribute to the average. All we end up with is this. Well, look, there's a lot of very similar terms here. We've got a 1/2 m a squared e to the minus 2 gamma t, 1/2 m a squared e to the minus 2 gamma t. So we've got an omega prime squared plus gamma squared. But what's omega prime squared plus gamma squared? If you look back at how we defined omega prime squared, that's just omega naught squared. What's omega naught squared? It's root k over m. Squared, that's going to give us a k over m, times m, that's just k. So we end up with the average energy is just 1/2 k a squared e to the minus 2 gamma t. Well, very, very interesting. Look at this. What is this? It's just 1/2 k times a e to the minus gamma t squared. It's just 1/2 times what we thought of as the amplitude squared. And that's just exactly the kind of energy we thought was stored, the potential energy stored in the oscillator, the maximum potential energy at its maximum positions, maximum displacements. Okay, well that makes sense. That makes a lot of sense. Very, very good. Well, let's think about this. What is going on here? What we have is that the average energy looks like the initial energy, 1/2 ka squared, times e to the minus 2 gamma t. So while the amplitude drops off as e to the minus gamma t, the energy which goes like the amplitude squared drops off as e to the minus 2 gamma t. It kind of drops off twice as fast. In other words, it drops off by a factor of e in, say, half the time. Well, let's look at this. Let's imagine that we go from some time t equals 0 to a time tau, where we want to choose what is the tau so that the energy drops off by a factor of e. That would be what we would consider the damping time. Well, at 0, t equals 0, we get an energy of E naught. At a time of tau, we get an energy of e to the minus 2 gamma tau. We want the ratio of this to this value to be e. So we want E naught over E naught e to the minus 2 gamma tau to be equal to E. In other words, bringing this up here, canceling the E naught, e to the, bringing it up, 2 gamma tau, we want that to be e to the 1. In other words, 2 gamma tau equals 1, or tau equals 1 over 2 gamma. There we go. That is the damping time, 1 over 2 gamma. So what we're going to do is we're going to rewrite 2 gamma as 1 over tau, and we'll rewrite this energy. So what we have is the average energy of the oscillator. And when we say average, remember, we're averaging over a cycle, an oscillation, is equal to E naught, the initial energy being 1/2 k times the initial amplitude, we'll call it A naught squared. So imagine you displace the oscillator to some amplitude A naught, the total energy, which is all kinetic, which is all potential, will be 1/2 k A naught squared. You release it, and then it starts oscillating. The frictional force removes energy, but the initial energy is 1/2 k A naught squared. The average energy then drops off as the initial energy, e to the minus t over tau. Tau is the energy damping time. Sometimes it's useful to define a quality factor, which is telling us basically how rapidly is the system losing energy, or the higher the quality factor, the slower it's losing its energy, where Q is equal to 2 pi times the energy over the amount of energy that it loses per cycle. So how much energy does it lose after one oscillation? Let's see if we can't figure that out. Differentiating dE dt, we bring down a factor of minus 1 over tau. So we have minus 1 over tau, e to the minus, whoops, I lost the e naught in there. E naught, e to the minus t over tau, which is the energy, e naught, e to the minus t over tau, negative over tau. So that e over dE divided by dE multiplied by negative tau, we have negative tau over dt. Or for one period, we want this for one period, that's going to be e over delta E for one period will be minus t over dt for one period is the period t. So let's bring this over here, and what do we get? We get Q is equal to 2 pi times the magnitude of this, which will give us tau over t. 2 pi over t, remember that is just the angular frequency. The angular frequency for the damped system is omega prime. So this is just omega prime tau. And that is the quality factor for the oscillator. Okay, very good. Now, let's take a look at the frequency. What's going to happen to this omega prime as we change the amount of damping? Let's see what happens.